Thank you, Chris. Hello, everyone. So I'm Thibault Lestang. I'm a research software engineer in the Department of Aeronautics at Imperial College. And I've got 15 minutes to talk to you about Python packaging, and it's too short. So specifically what we're going to do is that we're going to talk about the distribution of Python packages across Linux distributions, and we'll have a look at why it's actually more difficult than it sounds, and what are the current solutions, and we'll have a look at the trade-offs that they entail and the potential solutions. So can you all see my screen? It's a terminal. We just tested it, so I'm guessing yes. Okay, so it's going to be a fairly informal demonstration, and I'm just going to type some commands and just go through things as we go along. So the first thing about Python packaging is that it can be a little bit confusing because a Python package is two things. A Python package is a collection of Python modules, so it's a directory with .py files in it. But a Python package is also something that you can pip install. And so today what we're talking about, in order to clear all confusion, is that we're talking about what we call distribution packages. So basically archives that contain Python code and potentially, as we'll see now, compiled C or Fortran code. We'll have a look at an example package that looks like this. So basically, there's two things in this package. There's a CPP file, a C++ file, that basically implements a dot product. And the important thing is that it links to a C library. So you've got a CPP D dot module that has a dependency on a linear algebra library that's itself written in C. And then the other part of the package is the Python part, which is a module that makes use of this C++ compiled module. So this package is built by first compiling the C++ module, and then in the .prod.py, there's an import d dot that imports the compiled module. So in Python, there's basically two ways of packaging. The first one is what is called a source distribution. And you build a source distribution. Once you have your package in place, you build a source distribution by typing something along the lines of Python m build and then sdist. Sdist is it stands for source distribution. And it's going to go through that setup.py file and pyproject.toml, all of the metadata, and basically, to cut a long story short, what it does, it generates an archive that contains everything needed to build and install the Python package. So if we have a look at the content of this archive that was just created, then you can see that what it contains is basically the Git repo. So now I can, it contains some metadata, the pyproject.toml, the setup.py, the C source, importantly, and the Python source. So now I can take this archive, and I can give it to you, and then you can run something like pip install this archive to build and install the package. Now, the important thing to realize here is that the compilation, the build event takes place in your machine, right? As a developer, I just packaged the source. That's why it's called the source distribution. And I give it to you, and you have to compile it. You've got everything to compile it, but you have to compile it. And actually, I just lied to you because I said you have everything to compile it. Well, actually, you don't have everything because, as we saw, there's this dependency on the C library that you probably don't have on your system. So you'll have to install it, and you'll have to install the right version. So that was the old days of Python, when at the time of installing NumPy, for instance, was a pain because you had to compile a lot of Fortran code. But since roughly 2010s, this is starting to be a while ago now, there's another way of distributing Python packages, and that's called wheels. And we can generate a wheel in a way that's fairly similar. And it looks the same, but you'll notice that this time code is actually compiled. You can see that this is actually compiling the extension. And it gave me this wheel file, .whl. And if we have a look at what is in there, that's the content of the wheel. And you can see that it's a bit different. In here we have the init.py and the py, okay, but it's not in the source directory, right? Because in my package, it's within an src directory, and then the package is actually in there. In this case, it's really directly into the package directory, and then I've got my compile module right here and the metadata. So now I can give that to you, and then you can run pip install this wheel file. And the main difference with the source distribution is that no compilation will take place. Pip will literally, the only thing that has to be done is to extract this wheel file, which is essentially a zip archive, and put it in the right place. So typically your side packages, wherever Python packages are stored. So in this case, the compilation happened on my machine, on the developer's machine. And what I distribute, the artifact that I distribute is already compiled. Right? It literally contains a compiled shared library. That's the main difference between wheels and source distributions. Now, if you have a look at the NumPy PyPI for NumPy, you can see that actually you've got a source distribution and you've got a build distributions, and you can see that there's a lot of different build distributions, so little different wheels. And what I'd like to look into right now is specifically the case of Linux. Because for a wheel, you can see that I've got this compile binary. And let's look at this compile module in a bit more detail. So I'm going to extract the content of the wheel. So that's going to be okay. So in wheel content, and now if we have a look at so I'm going to list the runtime dependencies of my wheel. So it's in example package, and then d dot. Let me make it a little bit slower. Okay, so now we have a look at this, and we can see that so LDD probably stands for list dynamic dependencies, and we can see that this shared library at runtime it expects to find other shared libraries. One that we would expect, like the C standard library, the math library, but you can also, and these are provided by the system, but then you can see that there's also this dependency on the BLAS library, which is the C library that the module in my package is compiled against, right? So now if I give that to you, but you don't have liblas installed, then it's not going to work, right? You'll have to install the dynamic, the shared library. That's one thing. But the problem is, if I'm on the latest Debian and you're running Fedora, then probably both distributions do not package the same version of liblas, right? Maybe they do, but maybe they don't, right? Because different Linux distributions package different versions of the software because they maintain their own ecosystem. Even if I compile my code on Debian with liblas.so.3, then this compiled wheel is probably not going to work with an older version of Debian that packages version 2. Okay, so this wheel, is compiled on my machine, which means that you can install it without compiling anything, but it's not portable in itself. So there's something more that we need to do in order to make sure that this wheel can be portable across different Linux distributions. And that's the reason why this many Linux project came about, that you may have maybe heard of. You can see it here in the wheel tag, many Linux. And the many Linux, it's a set of policies that help make Python wheels portable. And so the basic assumption, very quickly, the basic idea behind this is that, well, making a binary portable is very difficult. But there's one thing that you can do, is that you can aim for the least common denominator. So if we're thinking about Linux distributions, what is the thing that will be there, that we can assume will be there in most Linux distributions? Well, the answer is the GNU C library, glibc, together with a set of core libraries that is basically summarized here. At some point, the Python Packaging Authority, which are the people behind Python packaging mostly, made a decision saying, OK, well, we're going to assume that these libraries are going to be present in all distributions. And the good thing with these core libraries on glibc-based Linuxes is that they are backwards compatible, which means that if you compile code against older versions, right, then it's guaranteed to work with newer versions. Okay. If you compile code against newer versions of glibc, it's not guaranteed to work with older versions, but the opposite is true, right? If I get a very old Ubuntu with a very old glibc, I compiled my binary Python package in there, it's guaranteed to work on newer Ubuntu because the GNU C library maintains backwards compatibility. So in practice, what does this mean? Is that, well, what you can do is that you can get a Docker image for all Linux distribution and compile your wheel in it, right? And so, for instance, if you go to the if you go to the mini Linux GitHub, they give you a set of Docker images with certain certain sets of core libraries. And so to give you a feel of what it looks like, basically here I've got a mini Linux Docker image that's running some version of CentOS that was released about 2010. Okay, and so it's got glibc 217. And what we can do is that we can build the wheel again in here. So Python. It's got Python in it, so I can build my wheel again. Maybe I need to remove something. No, all good. OK, I'm building my wheel. So right now, this wheel, it's still the same problem. It's linking to the library that I had to install in that Docker image. So in that Docker image, I still had to, I had to run yum install openblast to install the library. And so in this Docker image, there's a little utility called audit wheel, which does what it says on the tin. It audits a wheel, so I can say audit wheel dist a wheel and oh, sorry, I need to say audit will show. OK, and this is printing a sort of summary of what is linked against in this wheel. So it's linked against libgcc with these versions, the C++ ABI, but then you can also see libg-fortran and libquadmath, and these are dependencies of this linear algebra library. So these are not part of the core set of libraries. Right? So this wheel is consistent with the platform tag Linux, which is a generic platform tag, but it's not consistent with the mini Linux tag. So, and the last bit of the puzzle now is, OK, how do we make the wheel consistent with the mini Linux? How do we make it portable across many Linux distribution? Well, the trick is to take these dependencies and bundle them into the wheel. So I can say audit wheel repair my wheel, and this is basically going to take the wheel, take the dependencies, and then stick it into the wheel. And so now if I list the content of the wheel, I'm not going to do it now, but you could and look at the dynamic dependencies, you can see that in the wheel, the compiled module is actually linking to libraries that are within the archive. And so now this is sort of a self-contained archive that contains the binary module as well as the compiled shared binaries that it links again. So I can give it to you who's running an old Ubuntu, as long as it's newer than maybe 2010, and it's guaranteed to run. Okay. If you're running an Ubuntu from 2005, it's not guaranteed to run. Okay. And you have to get an older version of CentOS. Okay. So that's basically what I wanted to show you. I'll just finish with one little comment, maybe that opening the room for discussion. This obviously makes installing Python wheels much easier, right? Because before that, installing NumPy, for instance, or even if you're thinking about installing PyTorch, which is basically a big C++ library, is very tedious. That's the reason why Conda emerged, and I think Lester will talk about Conda now. But now, sort of the Python community kind of caught up with it. But if you think about what's going to happen is, yes, it's much easier, but then it means that you're packaging a lot of binary code into an archive. And so we have to think about the potential security implications that it means, because PyPI doesn't have a lot of people checking. Anybody can upload anything on PyPI, and so when you pip install something from PyPI, there's a good chance that you basically install arbitrary binaries on your system and you run code from them. So that's one thing to have in mind. And the last thing is maybe there's something to say about reproducibility, because much often, if you pip install binaries from PyPI, there is no provenance tracking, and there's no way of knowing actually how were these binaries compiled. There's no traceability of the build process, right? So these are things to keep in mind. But that's basically packaging compiled binaries, Python packages across Linux distributions in 17 minutes. Sorry for the, it's a bit longer than I thought.
That was brilliant, Thibault. Thank you very, very much. I think we all appreciate that talk, and I've learned a lot. And thanks also for pointing some discussion topics we can use afterwards. So as a reminder, we're going to have all the questions and kind of discussion topics right at the end, which will hopefully evolve into a nice live view discussion. The link to the Slido is in the chat, but as we go through, we'll be able to also sort of open up the mic to people who want to talk as well. But without further ado, I'll now pass on to Lester, who's going to talk to us about Conda.
Okay, great. Yes, my name is Lester Hedges, and I'm a research software engineer in Christopher's group at Bristol. And I primarily write biomolecular simulation software, and have been using Conda for probably since 2019 as the primary distribution method for our packages. And since it's the end of the week, almost weekend, I thought I'd have a nice feel-good story about how Conda is fantastic and makes my life wonderful. But unfortunately, that's not the case, at least in my experience. I don't want to bash Conda too much, because it is, it does certain things very well, and we certainly wouldn't be able to distribute our software to as wide a range of people without using Conda. But as a package maintainer, it's quite frustrating that such a large amount of my time goes into dealing with Conda issues, and a lot of them are not of my own making. So to start with, for those who don't know, what is Conda? So Conda is an open source, cross-platform, language agnostic package manager and environment management system. So it was originally specifically developed to solve Python packaging problems for the Anaconda Python distribution. And then it became a really useful tool in its own right. So, it doesn't just need to be used for Python packages. So they spun it out as a separate package. And it allows the creation and management of what are called environments. And these can contain, binary software, packages, source code, and library files. And so these are, user space environments that are self-contained and can be activated. So you could have, multiple versions of packages in different environments to do different things, and not have things clash. So a key point with Conda is it manages dependency compatibility when you're installing and upgrading. And this wasn't fully supported by pip until version 20.3. So this was something that Conda sort of had as a benefit. So what is it good for? So it makes it easy, and I'd say easy in quotation marks here, to set up quite complex environments which work across a range of operating systems. And it's a very useful way to install packages that might not be available for the native package manager on a particular OS, and then you'd have to install this from source. And at Bristol, for example, we use Conda as a way to set up environments for our teaching. So we can give instructions for users on different operating systems and know that everybody's working from a consistent set of packages within a consistent environment. It has sort of the aim of reproducibility. So in theory, you should be able to reproduce an exact environment. So, but in practice, this can be tricky and come at the cost of upgradability. And it's also becoming kind of the de facto package management system in quite a few fields. And it's even being used, even though it's an open source tool, it's being used by several commercial companies, particularly in my field, as a means to distribute proprietary software. So it's sort of become a necessary evil in many cases. Even though it can be painful, if you're not providing a Conda package, you're kind of missing out. So in my opinion, there's sort of three main problems with Conda. Conda itself, there's sort of issues with the technology, which is not particularly Conda's fault. It's designed for a particular purpose and it's grown way beyond its original scope. Conda packages. So again, this is community maintained packages. So people are developing and maintaining quite complex packages without really knowing the full details of the complexities of packaging. And then there's Conda end users who, again, are sort of installing these packages, but don't always understand the intricacies of Conda and the limitations of how to use it. So in my day-to-day experiences, some of the problems that I come across, and many of you may have experienced some of these too. First one is speed. So if you're ever trying to do anything with a complex, like large environment which has a lot of packages, you might find that Conda is painfully slow to resolve that environment. And Conda has a Python solver which has to search a very large, in many cases, and growing package index. And because of this idea of reproducibility, the old packages aren't removed so that you can still create or recover old environments in the future. And a lot of people tend to use Conda as if it's kind of like a rolling release Linux distribution where they'll have some environment where they'll keep adding new packages into or trying to upgrade that environment. It's not really the way that it's intended to be used. So, if you install one package, it has to resolve an environment for that package. Then you install another package, it has to resolve everything again and so on. And it becomes very hard to do that in a self-consistent way. So if you're doing something for a particular piece of work, it's much easier to resolve stuff in one go. So create an environment where you specify all of the dependencies in one go, and then you're giving the solver, a single task to do with us, at once, rather than sort of chaining together a bunch of Conda commands. However, it's become such a problem that external people have tried to solve this, and there's a package called Mamba, which I wouldn't be lying if I said that we could not do what we do with Conda without the existence of Mamba. It is a full C++ re-implementation of Conda, supports parallel downloading, and it uses libsolve, which is the backend for the RPM package manager for the dependency resolution. So it's much faster, much lower memory consumption. So once you install it, you can pretty much replace any Conda command with Mamba. Currently, might be a slight dependency resolution difference to vanilla Conda, but that is, that difference has got a lot smaller over time. So you can just install it into your base environment and use it, or they have their own environment container manager that you can use called Mamba Forge. Number two is space. So if you're creating environments, your local package cache on your computer can quickly become quite large, and this is becoming more problematic in my field since every single tool seems to start bundling on machine learning capabilities. So it's downloading different versions of CUDA toolkit and CUDA neural network and so on. So even, an analysis package which is a megabyte in size will pull in like 1 gigabyte, 1.5 gigabytes of packages. So it's not too bad on your own machine, but if you're on a space-restricted HPC resource, it can be a problem. So just looking at my Conda workspace here, I've only got a handful of environments for the work that I do, and that's up to 44 gigabytes already. Because in contrast, my entire root directory of my Linux install, which includes a backup of the previous two versions of every single package, is smaller than that. So, you can quickly run out of space. Conda has the concept of channels. So channels contain packages which are built against in a consistent way, effectively. So they have a consistent build system, consistent set of base packages on which they depend and so on. But you often run into situations where you might require packages from different channels. And if you do, there's absolutely no guarantee that they'll be compatible with each other. And you might find situations where the same package from seemingly compatible channels might not be compatible. So for example, you might have a different name for the same major minor version of a package, perhaps because they were built with a different build tool. So in this case, there's the default Conda Anaconda packages channel here, and Conda Forge, which is kind of the largest package database, two versions of GSL, which should effectively be the same. One has a minor version difference, but it's got a different name for the library. So if you can build your package against one, but in the dependency resolution Conda pulled into the other one, you'd be stuffed because you'd get an incompatibility. And you can solve this by pinning at the minor version level and so on, or having what's known as strict channel priority, where you say I want to exclude things from particular channels. But as a user and as a package maintainer, you don't really want to have to think about this and do this. You just want stuff to work as it should do. Another issue that I come across with Conda, and this is particularly in terms of how users interact with it, is there's a lot of black magic that goes on behind the scenes. So it's a complex program, and what it's trying to do and trying to achieve is very difficult. And the solver that Conda uses has scoring metrics that are used during install and update that aren't always transparent to the user. So for example, it first of all does what's known as a frozen solve, whereas it tries to find a version of a package that you've requested that could be installed that doesn't change the environment. So it won't upgrade or downgrade other packages in your environment, or could it find a package that's already in your package cache from another environment and so on. And so it might end up prioritizing locally cached packages, or trying to do things like minimize the number of changes to the environment. And the issue here is that you might, if you try and install something or upgrade, you might not necessarily end up with the most recent version of a package, and that could be what you want. And it's particularly an issue if your package grows in size over time. So for example, we've got quite large packages which add dependencies as we add new features, and sometimes we find users end up putting in an older version of our package just because it has a smaller number of dependencies, so would end up changing their environment less. There's ways around this again, but it's not always what you want to do or a reliable way of doing things. So I often find that I might end up trashing my local package cache just so it ignores that, or forcing upgrading of packages and so on. But that's not necessarily a reproducible way of doing things. Okay, sort of final issue. Well, getting on to final issues is environment. So this is sort of the big thing that Conda aims to solve, is having these reproducible environments. But in order to deal with the management of these, you have a trade-off between reproducibility and upgradability. So this is just an example YAML file that defines an environment. So we've got the name of the environment, the channels from which these packages are pulled, and the dependencies that are used. And then you can create an environment as such and activate it. So this is very easy to upgrade because you've not actually pinned any dependencies, you've just said the names of the packages. But it's terrible for reproducibility. So if you depended on a particular version of Pandas and then it installed a newer version later on, it would break your analysis or so on. So what you could end up doing is you can version your direct dependencies. So you could put in the explicit versions of Python and Pandas you used. So this is better from a reproducibility standpoint, But then these packages themselves have dependencies. So what about the dependencies of those dependencies? And so on and so on. So finally, what you can do is you could first create an environment. So you've created your environment with particular versions of packages that work, and then you could export that environment. So you'd get what's known as like a locked or a frozen environment, and that explicitly has, you know, all of the dependencies and their dependencies and so on of everything in that environment. So this is reproducible in a sense, but then upgrading this could, in the future, if you wanted to upgrade a particular version of a package, can be difficult or even impossible. And the result that you get from this export is OS dependent. So you couldn't create this and then share it with a colleague who has a different operating system, for example. And also there's been a long-standing bug in Conda, which means that when you do this export, these channels that are listed here are done so in a random order. So it isn't, you know, which could affect the reproducibility. So there's a way around this as well. There's this tool called Conda Lock, which can create a lock file, which is it does have the channels in the right order, and it also generates one for different operating systems. So then you could be on, you know, you could be working on Linux, for example, but create a frozen environment that works across multiple operating systems that you could share with people. And finally, one of the issues is, you know, inevitable dealing with a community-maintained ecosystem. So as I've said before, CondaForge is kind of the largest channel that provides you know, the widest range of packages out there. But even within this sort of a major ecosystem, there is, you know, there can be things that are a bit janky. You know, there's review process for these feedstocks, which become packages. But things break, and then you have to find out that they're broken and go and bug people to fix them. So this was one that we had to deal with earlier in the year. Someone changed their build system for this font config package, and that changed the so name of the library, despite the version not changing. And this affected about 30 packages, which manually had to be rebuilt against the new so name. And it took, you know, over a month. Thankfully, the one that we depended on, which was a dependency of a dependency, got fixed quite quickly, so it wasn't too much of a problem. But, you know, it took me a while to figure out why the build had broken, what had gone wrong, bugged these people, and so on and so on. Similar people do things in like non-standard ways. So in this case, there's the DLL for Windows that has been put in a non-standard path. And we just had to deal with this by, you know, copying it to the right directory where it should be, and so on. Okay, so finally, I've not really talked about Conda packaging, but, you know, based on what I've said so far, sort of considerations, when you're writing a package for Conda, you know, think about who it's targeting. Does it fit within an existing ecosystem? So there's this channel called CondaForge that I've mentioned, and then there's BioConda as well, which has sort of come out of the bioinformatics community. So it's much easier if you can fit your package within an existing community, because they've got all the build tools and everything set up, and there's, you know, good documentation and a good community behind it. If you can't do that for whatever reason, try to build it in a way that it's compatible with probably CondaForge, and they've got very good documentation and submission instructions and Docker environments that you can use to do your builds in. And then think about dependencies and dependency pinnings. If you're writing something that's pretty much a standalone application, then you can be very specific with your dependencies. But if it's a library that needs to work within this ecosystem, try not to pin things so strictly, and then it can be more flexible. So a problem that we come across quite often is people overpin, and then it makes it very hard if they don't rebuild their package very frequently, because other dependencies of ours will be updated against new versions, and then this particular package will be holding back being able to use those more recent versions. So that's more of like a general packaging problem, but I come across it quite often using Conda. So just sort of finally how we use Conda. So we take the approach of building it in a compatible way with CondaForge, but for reasons that just because of the complexity of our packages, and historically we've used a GPU accelerated tool, which wasn't supported on CondaForge, we've distributed via our own channel. So we have a very large C++ package that has Python bindings, And then we have another pure Python package that's built on top of that. So we have this complexity of needing to have a base package that's built in a way that's self-consistent with our other package. So we have, a lot of complex dependencies that we need to manage. And we also have users that want to be able to use our code in environments that have with and without some of our dependencies, which makes it also a challenge. And they also want to use it within larger environments. So we need to make it compatible with packages that aren't actually dependencies of ours. So Conda makes it a little bit tricky to deal with things like this because it doesn't really have the concept of optional dependencies. So you have to build it as if that package would be in the environment, but it's not needed at runtime. Okay, so that's kind of a whistle tour of Conda and some of the issues with it. I don't want to bash it too much because, as I say, it is, it does make our lives easier in some ways, and it helps us get our package out there to users. But things you need to be aware of.
Cool. Thank you very much, Lester. That was really brilliant. So, as I said, we're doing the questions for all of the talks at the same time. I think what I've just done is I shared it, then I unshared. Do this again. Joy of Microsoft Teams. Okay, there we are. Actually, be able to see the questions on the board. What I will do is we'll start sort of asking questions of the two presenters, but then I want this to turn more into a sort of open discussion. So if you want to talk or you want to also bring in your part, your sort of response to a question, also feel free to raise your hand, and then I'll let you open your mic, and we can hopefully make this much more open. So we're going to go with the first one that's at the top, which is if many Linux requires linking against quite old glibc, libstandard C++, is this quite restrictive on the language that you use? E.g., what if you want to write C++20? And I think, Thibault, do you want to give an answer to this?
Yeah, I think, I mean, it's a valid question. I think it's about portability, right? So if you want to use C++20, it's a choice that you make, but you then probably assume that the people who are going to use your software will have the right runtime libraries to use it. And yeah, so that's in this case you have to deal with that portability issue. Now, if you want to make it portable, then you have to go back to all the glibc versions that probably don't support C++20. There's no solution. It's a trade-off. What people do is that in this case with C++20, but otherwise you can go back to older versions of Mini Linux and do a Mini Linux, 2005, 2010, 2014. But yeah, there's no there's no like off-the-shelf solution for this. It's a trade-off.
Yeah, that's a really good answer. I mean, my experience is very much similar. That as soon as you go to C++, Mini Linux and pip become really difficult. And actually, that's the push to Conda. And actually, why we went to Conda is Conda's better at C++ kind of management because you have this multiple ABIs and it's a much more complicated set of libraries to link against.
And Nicholas in the chat just mentioned that you can actually compile a newer G++ or newer GCC against an older glibc, which you would do. So you would do that in the Mini Linux Docker image. You would compile GCC and then link in there. That's a good point.
Yeah. Well, and James, do you want to come in?
Yeah, I just wanted to follow up. Thank you for your answer and for the interesting talk. I guess the question actually leads me onto something that I think you've sort of hinted at, which is that there are different versions of Mini Linux. So there's different standards from different years. So I guess if you wanted to, is it true that if you wanted a more modern C++ standard, you could go for a more recent Mini Linux version?
Absolutely, yeah. So if you go to the Mini Linux GitHub or the PA Package Authority website, you'll see that they actually give you like a Docker image for every generation, basically, of Linux distros. And they had like Mini Linux 1, which is I think 2005, then there's 2010, 2014, and then they realized that it was a terrible idea to do this thing this way, is because you need to have a new policy every like 2 years. So now the new scheme is Mini Linux X_Y, and that's a minor version of glibc. So in the talk, I generated a wheel that's 217. So it's guaranteed to work on any Linux distro that has 217 and above. And so you can target. And so if you go back to NumPy and see that the wheel that they provide different versions.
Well, thanks. Okay, what I'm going to do now is I'm going to move on to this question from Anders, which I think covers, similar to James's other question, but don't want to just have questions from James, sorry. So you touched on this, I think, first to Lester and to Thibault. However, again, how would you describe commonalities and differences, many Linux versus Conda versus other, and when to use these? Lester, would you want to start?
Yeah, I guess I don't have too much experience of using many Linux, but from what Christopher said, it's not targeted towards a particular, it's not just Python, and it works a lot better with C++ packages, like building a compatible C++ package with many Linux is a bit more challenging than doing it within a Conda environment. As I mentioned, a lot of people do tend to use Conda as if they were setting up almost like a rolling release Linux distribution on whatever operating system they're using. So, for people using Windows, it gives them a way of accessing in an easy way a bunch of tools that they wouldn't otherwise be able to install. So it's it's almost like a more general purpose package manager.
Cool, thanks. And indeed, to be honest, one thing I would add to that is, and again, somebody can correct me if I'm wrong, I found that with Conda, the libraries are installed in a central place. So when you build Conda packages, you can link to another package's libraries that they've bundled. But when I've tried to use many Linux in a similar way, the many Linux libraries tend to be kind of in the same directory as the wheel, and it's hard to link between them.
That's right, yeah. So Conda has this central package resource that I mentioned in it, and where possible, Conda will just use hard links. So if you create a new environment and there's already a package installed, it will just create a hard link for that, if it can do, if there aren't any, hard-coded paths in the binary or anything like that. Yeah. So
it's probably the fundamental difference.
Yeah.
Yeah, it's also the source of all of the Conda problems, because this is why you end up with one library will change because of one package, and suddenly every other package on Conda is broken. Thibault, did you want to add anything to this?
Yeah, I guess, what's interesting to me is that there's a bit of history behind this, because I think I wasn't using Python at the time, but maybe early 2000s, I hinted on this, if you type, pip, or Python setup.py install, for NumPy, then you had a lot of red on your screen, saying you don't have like a C compiler, you don't have BLAST libraries, you don't have a Fortran compiler. And so I think at the time, installing Python packages was less common, and the scientific Python packages like NumPy or SciPy were just like, your administrator would install them, and then it's not for you to install them. And I think that's where Conda started, and they eventually made a business out of this, saying we're going to tackle this problem of making scientific Python packages easy to install, i.e. pip install NumPy and it's over. Well, Conda install NumPy and it's over. And we're going to solve the problem of multi-platform, which is multiple Linux distros, Windows, macOS. It's a really tough problem. And then the last thing is the dependency resolution as well, which is highly non-trivial. But so I think it grew from the fact that it was just hard to install NumPy, basically. If you listen to the Conda people like Travis Oliphant, who was at the beginning of this, they just say, well, you couldn't install NumPy, so we had to solve that problem for everyone.
Yeah, I remember the life of installing NumPy before then. So cool, I'm going to move, and actually I'm going to just open the floor. Anyone want to put their hand up and add anything to this question, or their own experience of the different packages? Maybe someone who's into poetry, possibly. Poetry is the package manager, not poetry as in writing poetry. I'm not seeing any hands. Okay, so I'm going to move on to a question which I think was quite interesting. This one here, this was quite cool. It was mentioned that you have to be aware of potentially malicious pip packages. Does the CondaForge channel also suffer from this problem? Lester, do you want to start with that?
Yeah, I'm not 100% sure how Conda Forge deal with security, but as I mentioned, there is kind of a review process that you go through in order to get a package on Conda Forge in the first place. So they have a what's known as a feedstocks GitHub page where you submit a recipe to how to build your package within their ecosystem, and there is a review process there, and people can look at the outputs of your build to see what it is. The issue is once it's accepted, I don't know what happens if you as a maintainer then go and change something, whether once it's accepted everything's on trust at that point, or whether Conda has some kind of way of scanning things or doing some rudimentary checks before packages go up to their channel. But yeah, at least there is a review system in place for the actual packages.
Well, I mean, I think James, do you want to give an answer?
Not an answer, but I thought I could make a contribution, which is that I think one difference is that on PyPy you can build a package locally and you can upload it, so you can compile the binaries on your local machine. I think that's the standard way most people do it. But on Conda Forge, I believe the only way a package can end up on Conda Forge is by building on their CI. So in a sense, that's a security benefit because there's an auditable trail of what's been done to that package. So there's going to be commits to the feedstock repository, even though it potentially could be a bit obscured because you could be pulling in binaries from somewhere on the internet. But somewhere there's going to be a trail of what's actually gone into that binary, which you could look back on. Whether someone will actually do that, it's unclear, but at least that's there. Whereas on PyPy, you can imagine someone could do anything they want to the binary before they upload it, and you wouldn't be able to necessarily look back at what they've done without actually reverse engineering the binary.
Yes, that is correct. So on PyPy, I mean, I upload packages to PyPy. There's not really any checking at all. I could upload any binary I wanted to at any time, and then you'd actually hand one package across to another maintainer when we did the transfer over, and there's this little window where effectively somebody else took over the name and could have done whatever they wanted with it. And I've heard quite a few attacks via that route. With Conda, my understanding is that the paid for channels, so from the Continuum IO, they actually do a lot of security management because people pay for that to go behind effectively kind of a allow list block. But for Conda Forge, I think it's just that it goes through it is run on their CI, and there are some levels of checks, and I think they have some security scanning, which Microsoft is now bringing into it, but it's not. I think there's still a lot that could be done in the Python ecosystem when you compare it to maybe other ecosystems like the R ecosystem, where things are extremely locked down before people can submit packages. Any other comments people would like to make on this question? Thibault?
If anyone, I'll give the chance for anybody else to speak because I have spoken a lot, but I do have something to say.
Go on.
Okay. Yeah, I think it's also we have to think about reproducibility as well. I think the Conda Forge setup is probably much better than PyPI. But at the end of the day, when you pull whether it's a Conda package or a pip package or a wheel, you still have fairly opaque binaries, and your project will be as reproducible as the binaries are reproducible, right? So if you pip install PyTorch, if you actually look inside, you'll find gigabytes of binaries, including OpenMP and some machine learning libraries. And there's no way to actually go to the source, right? There's no way to compare to make sure that binary, is the OpenMP binary the OpenMP, or is it like Google's version, of the binary? There's no way to know. And there's security, but there's also a problem of reproducibility in that sense, that the binary environment is not reproducible. And I would also say that you get a lot of, in PyTorch, for instance, if you pip install PyTorch, you are getting proprietary NVIDIA libraries that you would link against without knowing. And that's potentially a bad surprise.
Yeah, I mean, again, I think that's delve into a whole topic of the licensing and license contamination, which we talked about on the random channel, I think it was, or in general about Python. It's a whole can of worms, I think, when we start looking at linking together open source and proprietary binaries on users' computers. Okay, so we have 5 minutes left. What I'm going to go with is this question that's got 2 upvotes, just as an end with, and just before I even say people answer it, if you want to continue the discussion, go on to the hashtag RSE South, so that channel on the Slack, and the speakers will try and answer some of these questions, and I think I'll send them to them if they want to try and answer them later. But just to finish with, am I correct? Where did you? I clicked on the. Sorry. I've deleted the question by mistake. I apologize. I will move on to, am I correct in thinking binary distributions of packages from the default Conda channel are not licensed for commercial use? Anyone like to try and answer that question or even discuss commercial use of Conda binaries? So my understanding of that is that the binary distributions can be used commercially, but access to the repo, the place where you download it from, that access is kind of the thing which they try and limit. And now is it, James caught my question, so we weren't going to answer that one because I clicked on the wrong part. The question which I was going to do was, I think the question was, is setup.py, has it been deprecated in favor of pyproject.toml?
Haha, yes. Yes and no.
Yes and no, that was a very short question, in which case I can do one more then, just very, very quickly for this one. Minilink solves the Minilink solves the portability problem of glibc, etc. How does Conda solve the same problem?
Yeah, so similar for Conda Forge, they have Docker images that for Linux would be based on an oldish version of CentOS, and then the macOS builds would be targeted against a particular macOS deployment version, and so on. So they'll have some level of backwards compatibility with old versions of operating systems.
Cool. And then, because we just have one question and 1 minute, Lester said Conda does not offer optional dependencies. Does run constraint in meta.yaml not allow this, or is that something different?
So run constrained can work for sure. The issue that we run up against is not so much the optional dependency itself, but it's the fact that you need to say you've got an optional dependency which is it's a C program, for example. You need to build your package in an environment where that package exists, so that you have the possibility of a user installing that package in future. So it's not just the case of putting in a run constraint, it's the fact that you'd have to add it as a host dependency. So you could have something like a meta package which collected together all of some group of dependencies, which is what Conda does. They have an Anaconda meta package which gives you like the base packages, but it's just this additional complexity where we have users who might want to use some unknown package in future that then may be incompatible with our package, and then we have to add it in as an optional host requirement and so on. So yeah, for something that's just like a pure Python package, you could just add a run constraint, no problem.
Cool, thanks for that. Well, actually, we managed to answer all the questions we had. So thank you to both Lester and to Thibault. Very, very fascinating. Thank you all for the discussion. We're going to try and organise another one of these webinars in January. If you have an interest in a topic or you want to volunteer to speak, please go onto the RSE-South channel on Slack. Equally, if you want to continue this discussion or you want to link up with other RSEs in the south of England, go onto RSE South and have a chat with everybody. Other than that, thank you everyone for coming, and I think that was quite a successful first webinar. Enjoy the rest of Friday.